Thank you for joining me on this lecture on law of mass action. So essentially the chapter 6.2.3 in our course in solid state physics. And although I will never know that you have actually listened to this lecture, I'm pretty happy that you are doing it, because the law of mass action is quite fundamental in order to understand properly how semiconductors behave. So this is actually quite useful piece of mathematics that we will be coming to terms with in this lecture. So I'm very happy that you're joining me in the derivation of the law of mass action. So essentially, what we will do here in this lecture is that we will derive this mystical sounding relation, and that's a very useful relation to understand the electron and vacancy populations and their interdependency. And if you're interested in the kind of nomenclature here, I believe that this name comes from the chemistry, because it sounds a little bit muddy, murky, like what is that? What does it mean, law of mass action? But I think the name comes from the fact that this kind of similar equilibrium dynamics also takes place when we would be looking chemical reactions, and especially their reaction rates. So in this piece of mathematics, we're dealing with the statistical processes, and this is very much related to the reaction kinematics. And in case you're more familiar with chemistry, which of course would be sad, but if you would be, then maybe you would understand that the kind of name of this relation is coming from this kind of historical concept, or a historical point, that the similar piece of mathematics is also happening in chemistry and reaction rates of some processes. And once we have done the derivation, we will also see that the chemical potential, so this mu, essentially our Fermi level, that how we can really link that to the effective masses of our electron states and the electron vacancies, so holes. And this in a way implies to us that the band structure engineering, if you could do that kind of modification on the material, for example, by having a ternary compound semiconductor, then we could also adjust the Fermi levels accordingly. So essentially the effective masses could be adjusted with that kind of tricks. But please note that in our course, the focus is really on just the 101, so kind of doping of semiconductors and how we can use that to change the properties of semiconductors. So we are not that much interested in the actual kind of knowledge of how the band structure in itself of a semiconductor can be adjusted. But this is my brief introduction, and let's now get actually started. So what we will do here is that I will try my best to derive to you the law of mass action. And as we can see in the earlier lectures, we noted that the variables, the electron and hole concentrations, so N and P terms, they of course are temperature dependent, and this is something that was obvious in the equations we derived earlier. And this is the case for intrinsic semiconductors. So we have not yet considered doped or extrinsic semiconductors here at all. So these are perfectly okay for undoped semiconductors. And now what we will find out is that we will want to describe N and P without any information of the actual chemical potential, so that we want to kind of figure out how we could understand how we could calculate or estimate the number of charge carriers, so essentially N and P, as a function of temperature only and not as a function of chemical potential as such. So this is what we're kind of interested here. And chemical potential here we really equate that's equal to the Fermi level, but there is some subtlety regarding the terminology, but we deem that to be beyond our course. And here, what we will also see at the end of the lecture is that this chemical potential mu, we can really link that also to the effective masses of our electron states, so Me star, and into the effective masses of vacancy states, so Mh star. And the logical starting point that we want to start with our derivation is that we just note that the band gap value Eg, of course, that's the difference between the Ec, the smallest energy value we have in the conduction band, and then the largest energy value we have in the valence band. So this is of course the energy band gap that we have in the semiconductor. And with this, we can simplify our product. So we have already come up with the equations for N and P, and now we are just mindlessly calculating their product. And then what we get out is that we can place this simplification for the Eg into these equations we have derived earlier. So we have this exponent mu minus Ec per kPt in the term for the N, so the density of electron states, and we have the same equation for the density of hole states in the valence band, and we have there the EV value here. And now we just multiply things, and we can see that we can simplify notation by use the Eg value. So we are left with the NFC and NFV values, parameters, and they of course depends also on the temperature, but not as dramatically as the exponent. And then we have in the exponent EV minus EC per kBT, and this is of course equal to the Eg value as we see in the earlier equation. So essentially, like we have these terms, and then we can just write the exponent as a exponent minus Eg per kBt. And plugging in what we have discovered from the capital N parameters, we can write that the NP term is equal to 4 times kBt per 2 pi h bar squared to the power of 3. And then we have a term that depends on the effective masses. So we have the effective mass of an electron state, Me star, times the effective mass of a vacancy state, Mh star, to the power of 3 over 2. And then we have the exponent over the minus Eg per kBt. And this, in a nutshell, is known as the mass action law. So it's not overly complicated looking equation, and the derivation was just brute force multiplication of things that we have already discovered. But oh boy, this is actually useful when we want to understand the kind of conductivities and operate things, especially when we're dealing with intrinsic semiconductors. So we have the temperature dependence on the first term, and certainly we have the exponential temperature term here. And we see that we also have this NP product depending quite sensitively on the band gap value. And here, of course, we have the effective masses here, so also their values affect the actual MP value. So let's now look what this implies in terms of other parameters that we could estimate or used to estimate the properties of our semiconductor. So we are still dealing with intrinsic semiconductors, so we are not doping semiconductors at all. And in this case, physically, what must be the case is that the electron and the hole concentrations, they are equal. So what this means physically is that when an electron in the conduction band is being, or when an electron is being lifted into the conduction band, it must leave behind a hole. This is physically what must happen. So essentially in a figure, like hopefully that clarifies what happens. So we have a semiconductor we are dealing with, and when an electron is being lifted from the valency band into the conduction band, well, we must have a hole state left out in a valence band. And at all times, since we are dealing with an intrinsic semiconductor, like the electron must be there somewhere and it must leave behind a hole, it means that N and P must be equal at all times when we are dealing with intrinsic semiconductors. And this is what's happening in intrinsic undoped semiconductors. And since this is the case, we can just label that this intrinsic carrier concentration of electrons, N, we can label that with I, as in the case of intrinsic, and that must be equal to the intrinsic carrier concentration of vacancies. And this is, of course, we can calculate that it's the square root of the product of N and P that we just discovered. So basically the square root of mass action law. And this must be equal to 2 times kPt divided by 2 pi h bar squared to the power of 3 over 2. And then we have the term depending on the effective masses. And then we have the exponent minus Eg per 2 times kPt. So please note we take the square root. So we have the 2 here also in the exponent also as well as in the other exponents. And this is something that actually tells us quite easily that how many electrons we have in the conduction band, and at the same time it also tells us how many holes we have in the valence band. And when we are at the moderate temperatures, so we are not at very high temperatures, these variables, these values are quite small. So Ni is quite small, and Ni of course equals Pi. And this means that at moderate temperatures, at room temperature, these kind of intrinsic semiconductors are poor conductors, so that we don't have many carriers that can participate in the macroscopic electrical conductivity of a material. And this is why intrinsic semiconductors as such are not very useful in terms of applications and making electronic devices, because they are not very good conductors, and we cannot easily modify their conductivities neither. So that's kind of the motivation to move in future towards doped semiconductors. And as I promised, finally, we will use the mass action law and find out a slightly different relation just using the equations we have derived. So we want to basically show that the chemical potential mu, so equally essentially here to the Fermi level, that this is linked to the effective masses of Me star and Nh star. And how we do that is that we don't multiply P with N, but rather we calculate the ratio of P over N, and we just see what comes out. And now we are left with a little bit of simple algebra. So I don't go into the details. There's nothing strange in here. We just vanish. We remove the terms that are equal in both sides. And what we are left with a ratio of the effective masses to the power of 3 over 2. All the rest of the parameters vanish. And then we are left with an exponent where we have now 2 times minus the chemical potential plus EV plus EC over kPt. And now we can simplify this notation slightly further. These energy values, they are somewhat arbitrary, so we can just denote that EV is 0. See, we kind of scale our energy ladder to this kind of value so that the EV value equals to 0. And then what we get out is that then the EC value will be EG minus EV. This is of course always the case, but now since EV equals 0, then EC must be EG. And this helps us to simplify our equation that we had for the ratio of P over N. So we have exponent, and now we have 2 times the chemical potential mu minus Eg. So we just replaced Ev plus Ec with this, and then we have this divided by kPt, and this is equal to the fraction of m star h over me star, and this to the power of 3 over 2. And then we take the logarithm of both sides so that we can clean up this equation slightly. So we have on the left-hand side now 2 times chemical potential minus Eg per kPt, and then on the left-hand side, on the right-hand side, we have 3 over 2 times the logarithm of m star h divided by me star. And now we can solve this for chemical potential, so essentially our Fermi level, so that the Fermi level equals to Eg per 2 plus 3 over 4 times kPt times the logarithm of the effective masses. And this is actually quite nice, because we can, for example, just place in a value that, let's assume that we have a T equals 0 kelvins. So let's actually calculate the Fermi energy of our system. And now when the temperature is 0 kelvins, the second term vanishes. And what we are left with the fact that the Fermi energy, so mu equals really exactly Eg over 2. So this means that the chemical potential really is indeed in the middle of the band gap at 0 temperature. And then of course, like when we start increasing the temperature, we see how this Fermi level, the chemical potential, actually changes as a function of temperature. And if you really know, for example, the effective masses, if you know the temperature, and if you know the band gap value, we can really also estimate where the Fermi level is. And this is quite neat. please remember the picture that we had and discussed in our earlier lecture regarding the chapter 6.1, where we had these differently doped semiconductors. And there, essentially what changed was the relative level of the Fermi level with respect to the conduction band and valence band. And looking at this equation, we are now seeing that when we change the temperature, or if we keep the temperature at the room temperature, how we would be able to modify the chemical potential is that we would somehow, in the case of intrinsic semiconductors, be able to modify these effective masses. But we will soon learn that there is a kind of cleaner way, easier way of adjusting the chemical potential, and that can be done by doping of materials. But at least you now appreciate that there is also this kind of possibility of adjusting the chemical potential. And why this is neat, why this is cool, of course, is that this would allow us, for example, to calculate things, and then perhaps more interestingly and importantly, we could engineer things. So we could engineer the location of the chemical potential by kind of controlling the effective masses. So either way, like we could calculate the location of the chemical potential by knowing the effective masses, or we could engineer the location of the chemical potential by controlling the effective masses. So this gives us quite a bit of control knobs in terms of controlling the properties of our intrinsic semiconductor. So this is now what I had to say, and I will end up by saying that the law of mass action also works with the case of extrinsic semiconductors. Maybe the connection is not trivial how that actually works, but that's what I've been told, that it does work, and that would allow us to also solve the carrier concentrations in the more arbitrary scenarios. But I think this is way beyond our current scope, because we cannot really analytically solve those carrier concentrations, but rather we should do things numerically. So maybe we don't go into that kind of details in an introductory course. But now at least you know the basics, and we have covered what we must know regarding intrinsic semiconductors, so semiconductors that are not doped. And in the upcoming lectures, we will generalize our treatment to doped semiconductors. So these are also known as extrinsic semiconductors. And we will see that in fact, by doping the semiconductors, there's even easier way of adjusting the chemical potential and affect the carrier concentrations. And this is really done by doping of the material. So I thank you here. And I wish you a good day, and please join me soon when we start discussing doped semiconductors. So thanks and bye-bye.